What's antimatter?
I don't have the English for that, I believe. I don't think
You can try with Google Translator if you want.
Okay.
But do you know something? Yeah, go.
Something not being.
No, it sounds like very exotic, no? Like very mystical, no? Antimatter, wow.
Because I feel like matter is something that is.
Yeah.
So antimatter should be something that isn't.
Yeah, this is what I thought also. You know, like logically sounds like that, but no. Tell us.
Maybe unstable in a way that the atoms move or like.
Yeah, antimatter is more unstable, but it's not the meaning. Antimatter just mean you have matter, and antimatter is matter with the opposite charge, electric charge. Just that. But they call it antimatter, and it sounds very exotic, you know, but it's not exotic at all. So, okay, basic physics. You know this?
Not all.
Have you seen this image before?
No, I did not.
So this is the standard model of elementary particles. This is all the particles we know the universe is made of. There are 30 particles, so maybe you've heard quarks. I speak a lot about quarks. Quark is what the proton and the neutron are made of, and this is like this is particles mean is you cannot divide it anymore. It's like the last division of the universe. Like they are not made of anything or anything else. It's the last division of the universe. So yeah, this is maybe very confusing, no? If you've seen it from the first time, like at least for me when I saw it. So we have like these three, like this is matter, all these 9. This here, this 9 here, it's antimatter because they have the opposite charge. Here you see the charge, so it has like 2/3 positive, and this is just the opposite, up, anti-up. But it's the same, it's just a particle. And then here we have the bosons. They carry the force, the 4 universal forces. You know the 4 universal forces?
Correct.
Hmm?
The Turkish one, yeah.
Tell me.
Not to tell. It is the like push and pull, maybe.
What?
Say it like that.
What? Can you repeat?
Push and pull, like the force.
No.
Says
I mean, yes, about the name
the
of.
elements.
Yeah, they push and pull, but what's the name?
I don't know.
You know? So we have electromagnetism. So this is basically electricity. So this force is on this one, you know, no? The photons. Photon, the light, no? So this carry this force of the universe. Okay, the next one is a strong nuclear. This force is in this one, gluon, no? This comes from glue because it glues the quarks together. And we have weak. This is more like technical, also the another force with the atoms in the nucleus. This one is in this and this and this. And this became very famous, the Higgs boson. Have you heard like news about this? No? You remember like it became very, very famous in the scientific world. So this is called the particle God, because this particle is like give a mass to every other particle. It's like this particle allows other particle to be born. This is why they call this particle like the God particle, because it's like allow the other particle to exist, more or less. This is like a very simple image. I'm not physicist, so yeah, I'm explaining like the best I can. So which 4 is missing? We have 4 universal forces. You can explain everything with these 4 forces, like how everything interacts. You know which one is the topic of today?
Gravity.
Yeah, gravity. So why is it so complex? Because gravity is not a particle, no? Everything is explained with particles, but not gravity. And this is why it's so complex and we still don't understand. So you can think like gravity is the box and the particle are inside. It's like, yeah, like gravity is the structure and it's tell the particle how to move inside the structure, more or less. Okay, so this is like a resume, a summary of the previous image. No, you know this. What is this? These are the quarks, no?
Yeah.
And these are the gluons. So the quarks are glued together through this force, the strong nuclear. And if you have up, up, down, you have a proton. If you have down, down, up, you have a neutron. Then the proton and the neutron are also glued together with, yeah, this one also, but it's like another particle here. And then we have the electron. And this create an atom, the famous atoms. You know which atom is this in particular? The most basic atom. You know? Hydrogen. Good. Okay. And this one, why this one is not trapped here? No? Why is it this one is not attracted by this force?
Because it's like minus.
Yeah, but this is what is attractive because this is positive,
Yeah.
this is negative, so they are attracted.
Yeah, but like it's too fast, so it can stay like something like that.
Yeah, they say like this particle doesn't interact with this force, so it's like apart from this force, and this is why it can be outside the nucleus. Okay, so where is the mass in this picture? Like the mass, you understand mass?
Proton and neutron.
Where?
And proton and neutron is the mass.
But proton and neutron, there are many things inside. Where?
Right.
You know? So they are not like mass is a very technical term, no? For us in the street, mass is how much do you weight, no? Like you weight, I don't know, 60 kilos. This is your mass. But in physics, mass is not that easy. Mass is something that changes all the time. It has many definitions, it's very complex. So as far as I know, there are two types of mass. The intrinsic mass is what we think of mass when we think, no? Like intrinsic mass is this. We feel we are touching something. So this is what we call intrinsic mass, and it's every particle, no? Every particle has something, no? It's, you can imagine it's like a point, no? With mass, with something material, no? Something you can touch, like reality we see. But that mass is only 1% of all the mass. So where is the 99% of the mass if it's not in the particles? Yeah. Yeah, no, like if there are two things, so it has to be in the other one. So yeah, like for physics, the mass is not like material, is energetic. So we have intrinsic mass and energetic mass. So 99% of the mass of an object is not the particle, it's all the energy the object has. So the gluons, like the strong nuclear, like between the proton and the neutron, between the electron and the proton, no? This one electromagnetism. So all the energy accumulates. So in a sense, you can think of mass equal energy for us. It's almost the same because this is very, very low. So when we are talking about mass, we are talking about energy. This is important because, you know, gravity, we always say like the more you weight, the more attracted by gravity is. But you can also think that the more energy you have, the more affected you are by gravity. So it's the same. Okay, have you ever thought about this question? You know, no? The Einstein formula,
Yeah.
and you know they say light has no mass. Have you heard this? No? No? You? Maybe? So if it has no mass, why does it have energy and it's affected by gravity? No? Because if you put a zero here, energy equals zero. So how can light have energy with this equation?
Then it's not zero.
It's zero, it's
It's
zero, I
zero.
can confirm it.
No, I don't know that.
Yeah, it's because this equation is like the famous one, but the complete equation is like this. I think it's like this. No, no. Yeah, like MC4. Yeah. So if this is equals 0, no, then you remain only this. No, this is also this, I think, yeah. And then you take out the 2, no, this is basic math. So E equals PC. C is the speed of light. You know this, no? C on the C. And P, you know what P is?
Potential.
P is momentum. Momentum means you are moving. So light has energy because it's moving. So you can calculate the energy of light by the because you know it's positive because it's moving and you multiply by the speed of light. It's not the speed of light, it's the speed, the maximum speed you can reach in the universe. And to reach this speed you need to have zero mass. This is why light can reach this speed. But technically it's not the speed of light, it's the maximum speed of the universe.
So does this formula only stand for light? And that would be used for whatever else?
You can use it for anything. But yeah, like this is the complete one. Okay. So it has energy because of this formula, and also it is affected by gravity because it has energy, and as we said before, energy equals mass. So this is why if you have energy, you interact with gravity, with the structure of the universe. Okay, so this is why I brought the ball. So the first thing to know about the universe is we are talking about a curved space-time. This is not like the whiteboard, no? This is a plane space-time, you can say. And in a curved space-time, everything changed. Like the high school rules of geometry we learned, they don't apply anymore. So, for example, in a plane space-time, two parallel lines always stay parallel. But in a curved space-time, you see these two start parallel, but they converge, no? But they never move direction, they are straight. It's like this, it's a straight line. But they are moving in a curved space-time, so because of gravity, they converge. This is, for example, one thing that changed in this space-time. Yeah, like the center of the whiteboard, where is it?
In the center.
Here, no? Over here, no? More or less. Okay, where is the center of the ball?
Inside of it.
Like in the surface.
It's not on the surface.
Yeah, like the center in the surface. No, this is the surface. So in this surface, this is plane surface, this is curved surface. Where is the center in the ball?
Anywhere.
Yeah, no, like anywhere is the center. This is the center because everywhere is the same, no? Like this is the center because it's like the distance is the same, no? From every point. So in a ball, everywhere is the center. This is why also maybe you've heard like anywhere in the universe is the center. Because anywhere in the universe is the same distance from everywhere else. So this is why it changed. And this is what happens to Newton. Newton thought, because if you take, like in the ball, if you take just a little bit of a square, it looks like plane, no? But Newton thought the Earth was plane, no? Because like this floor looks plane, but if you look at it in a universal way, it's curved. So this was one of Einstein's mistakes. Okay, so why is Einstein considered a genius? Because he was one of the first persons to describe mathematically another dimension. Do you know which dimension?
Third dimension? Again.
Yeah, but what's the name? It's the fourth, but what's the name? It's not, it's easy. It's not something like, wow, it's just time. Because time. Einstein was the first person to describe mathematically time, because before Einstein we didn't know what was really time, or we didn't know a way to measure time. No, we said 1 second, but what is 1 second? And who choose what's 1 second? No? Like who was the standard for 1 second? So like to understand it, for example, like look at this shadow, no? Here, the shadow is 2D, no? 2 dimensions, but a 3D object is projecting a 2-dimension shadow, no? So Einstein was the same, like looking at this, a 3-dimension wall, he had to understand a 4-dimension wall, something that was, as you can see, very hard, no? Because it's like you can see the shadow and the 3D object, but our mind, it's impossible to imagine another dimension. So the only way to imagine another dimension is mathematically. Like our brain is not prepared at all to think about something for this. You can only do it 4 dimension. Like they say, like Einstein had, like he saw everything in a very geometrical way. Like there are some people that are born like this and they see like everything in a very geometrical way, mathematical way, and this is why maybe he could do it. So I brought you this image because maybe you have seen the image like without these three, no? Like only this, no? Like the sun is deforming something under it, no? Have you seen this image? No? No problem. Better. Because that image is wrong. Because that image makes the impression that like that gravity is like a force pulling you down, no? Like this is what they always tell, like gravity is something pulling us down, no? But it's not like this. Gravity now is like a deformation of space-time. And it's not just deforming space-time down like in the classical picture, it's deforming space-time everywhere. So it's not down, like you right now, you are deforming space-time up, left, right, everywhere. It's 360, it's not down. Okay? That's important to understand. Okay. Do you have any question? I'm going too fast, maybe?
No.
Good? Everything until now? Good. It took me a lot of time to understand this. But yeah, like, I consider I understand something when I can explain it in a very simple way. But it took me a lot to understand that. Okay, so this is the image that made everything click for me. Like I am very thankful for this image. So this image explains why Newton thought gravity was a force pulling us down, but in reality it's not a force. There is nothing pulling us down. We are just deforming space-time. You know, like this is a structure, and we are deforming it, but we are not attractive to other masses. Like we don't have an internal force inside us. This is very important. Like this is the difference between Newton and Einstein. Like Newton said, gravity is a force, but according to Einstein, gravity is not a force. It's not like magnets at all. It's something different. It's not a particle. It's like the structure of the universe. So why Newton thought there was a force, like a fictitious force? No, this is the same as when you go on the car and you are like turning a curve and you feel something, no, is moving you in the opposite direction, but it's, nothing is moving you. It's just, they call it like the frame of reference. Like if you see from outside the car, you see like nothing is moving you. It's just you feel something, but it's not true. It's a fictitious force. It depends on the frame of reference. So here we have two frames of reference. We have 1 and 2. Okay? The first one is you are inside an elevator. So if you are inside the elevator, you don't know if the elevator is moving or not. No? So you think the floor is still. You think you are like right now, no? We think the floor is still. But if you are outside the elevator, no, you know the elevator is not still. The elevator is moving. Okay, so I think the first one is called inertial frame of reference. Inertia. Let's write it because it's important. What do you wanna? This is very important because what's the name of Einstein theory? the name of Einstein theory. What's the name?
The theory of this?
No, like his theory of everything. General relativity. No, why? Because everything is relative. No, literally everything depends on your point of view. So Einstein was one of the first persons to mathematically prove everything depends on your point of view, even space and time. So we have two frames of reference, like inertial frame of reference, inertial frame of reference, and we can think of this as still, like not moving. This is how I think of it. I don't know if it's accurate from a physical point of view, but this is what I did to help me understand. And then we have this one, frame of reference. And this one, you can think of it as moving. Reference, this is moving. Or I think it's like the technical term is accelerated, but yeah. Okay, so if you are here, you are in an inertial. You think you are still, but the one here is non-inertial because he thinks he's still and he knows this one is moving. So if you drop a ball inside the elevator, to calculate how much the ball takes to arrive to the floor, he has to introduce a fictitious force for his equation to work. But if you are here, you can calculate how much the ball takes to reach here without using this force. Because when you calculate something and you are moving, like from our human perspective, it seems there are something acting upon you, but it's not. So the thing is, you can calculate the ball with both systems, perfectly accurate. But for this system, you have to create something that doesn't exist in reality. So this is what happened to Newton and Einstein. Newton was here. Newton thought the Earth is still, but what happened? There is something still in the universe. Everything is moving, no, in the universe. So Einstein was outside the elevator, and Einstein explained gravity without recurring to this force, because Einstein realized like there is no inertial frame of reference. Nothing is still in the universe. Everything is moving. So when you take into account everything is moving, and he tried to explain, he became with a totally different theory. Do you understand? Good. I'm happy. Okay. Yeah. I think that's all. Perfect. make me make this question. I think a lot about this question when I started understanding gravity, like how much of our experience is just a human artifact that doesn't exist, but it does represent reality. No, because now we know, like Newton theory is not completely wrong, but like the base of it is completely wrong, but it's totally represent, no, the world. Like everyone thought Newton theory was perfect. It was represented everything. So, but now we know it doesn't exist. So, how many things we think that represent reality, but it's just a human invention? No, for example, time for me. No, we think time is movement, but maybe no, we are inside the elevator and we don't know what is time from outside the elevator, no, because time is movement. No, what I said before, if you are moving, like you need to introduce fictitious force to explain your reality, but maybe like what is time outside our reality. So maybe there are many theories that says like nothing is moving, everything is still. Like we feel time as movement, but we are not moving in reality. Also, like another artifact very famous is like every day when we look at the sky, we see the sun going from east to west. No, and how people explain this before. No, like in the past, 1,000 years ago, people look in the sky and they saw the sun going to east.
The sun is moving.
Now the sun is moving, no? But now we know we are moving. No, but this is the same, no? Literally nothing changed. No, the both theory are perfectly like represent reality. But now we know like the sun is not moving, we are moving, no? But nothing changed. We are looking at the same sky as 1,000 years ago. So yeah, for me this is very curious, how the same point of view can have the two opposite theories, and they are totally like represent reality, but only one is true. Okay, this gift also helps me a lot to understand Newton and Einstein. So, yeah, let's take the ball. So we have here an apple, no? An apple. Let's explain Newton before. So when the apple is standing on a branch or on my arm, you can say, you have the upper force, no? This is my hand holding the ball up, no? And you have gravity, no? Gravity is pulling the apple down. So according to Einstein, when you release, there is another force, no? Making the apple go down. But according to Einstein, because this is you can think plane space-time and this is curve space-time. But according to Einstein, when you release the apple, you see there is no force. There is no force, like no gravity, nothing is pulling the ball down. The ball is going on a straight line, no? Because there is no force. It's not a straight line because it's going straight. Like if I do this, it's also a straight line. Although you see like a curve, trajectory. So this is very anti-intuitive, like how it is a straight line. It makes no sense. So the way I have to rationalize this is when you drop the ball, like the ball stays here all the time. What you are seeing is literally the universe moving around the ball. No, because we said nothing is still in the universe. So the ball stays here, but you can think of it like literally the floor is going up. Because the whole universe is moving around the ball. This is how I think of it to understand this. Like it's going on a straight line and there is no force. Because like like forcing, when you force something, like you go, if you do this, I am applying a force. But when there is nothing, it goes on a straight line.
But how about the weight of the ball?
What with it?
Like, it is something that makes it go down, no?
Yeah.
So, ain't that the force?
No, but not go down. It makes no. It goes down at the same. No, like the weight is not important for how fast you go down. Like they make an experiment in the moon, and they drop like a hammer and a feather at the same time. No, our logic may make you think like the hammer go faster, not than the feather, but no. In the moon, you can. There is a video. It's very interesting. Like the feather and the hammer go down at the same time, and I think it's related to this also. So it's not about the weight, because the weight was like a Newton, no? Because according to Newton, no, like the mass multiplied by the gravity, no, makes you accelerate it. But no, this is not anymore. Now there is no force. It's going on a straight line. Okay. Any question? Any commentaries?
So at the beginning we thought like mass is energy.
Yeah.
So when we look at it here, so like not in the moon but in the earth, if we drop hammer and a feather at the same time, obviously hammer will fell first. So do we think like mass creates more energy for it to do so? Or is
I
it
think in the earth the hammer goes down faster because of the air. But if you do it on a vacuum camera, it's the same.
yeah, so it's the mass that does that in that sense, or like gravity
No, I think it's like the air resistance,
or resistance.
because the feather, like the air make the feather not go down, but it's going down at the same like speed, you can say, as the hammer, or the same, I don't know, like the technical physical term. Yeah, the same. Yeah, I will play that video maybe later if you want. It's a very interesting video. Okay, this is, yeah, I need the ball for here also. So I'm very proud of this. I did this image. So as I said, all the image, every image you see of trying to display space-time is wrong. Is because you cannot paint 4 dimension. It's impossible to paint 4 dimension. So and your brain also cannot imagine 4 dimension. So our eyes are not made for 4 dimension. So every image is wrong. Even like that. For me, it's very helpful to understand Einstein. Okay, so in this axis we have time, and time is the only thing we know has only one direction. No, it goes from the past to the future. So if you go like this, you are going to the future. Okay, now we have a ball here. This ball, let's say. The ball is standing still. Bueno, first, what's a dimension for you? What do you understand for dimension?
Time.
Eh?
Time. We have time and the.
Yeah. And what is it?
Like a way to measure something.
Yeah, that's it. No? Because many times also dimension has like a mystical connotation, like the 10th dimension or whatever, but dimension is just something you can measure. Yeah. So according to Einstein now, there are 4 dimensions because he invented a way to measure time. Okay. Okay. So yeah, here we have the dimension of time, and here we have the 3 spatial dimensions, no? Like width, length, and height. I think. So we have a ball standing still. Is the ball moving?
Yes.
Yes. Why?
Because everything is moving.
Good, but in which dimension is moving?
In the 4th.
And that is?
Space-time.
No, only one. of those two. No, it's moving in a space, the ball.
No.
So it's moving in time, because everything is moving in time, no, all the time. So this ball here is like still in the space dimension, but it's moving in time, no. This ball is going to the future right now, as you are, and everything is. Okay, so the movement of the ball in the future is from here to here, no, from t1, you can say 1 second, 2 seconds. So the way it's not like Einstein, like after Einstein many scientists did a lot of like, how you say, addendums, I don't know, addendums, you understand? Addendum is like they added new things to Einstein theory. So I think this theory is particularly to Bukowski, I think. Bukowski, yeah, something like that. Okay, so the movement of the ball in time is from this to this, no? So it's this arrow. But what happened with that arrow? Like, let's here, like, you can say from here to here there are 10 meters, no? And according to that arrow, from here to here there are 10 seconds. So what is the difference?
I don't understand what you mean.
Yeah, like we said, no? A dimension is something you can measure. So the same you can measure from here to there are 1 meter. You can say from here to the future, or from here to there is 1 second. This is what Einstein created, like a theory to measure time. So what is the difference between this measure and this measure?
That's if it's moving in time, it doesn't have to move in space. But if it's moving in space, it's moving in time.
No, they can move on both.
Like it doesn't have to.
Yeah.
That's what I said.
But what is the difference between this and this?
That in time, it doesn't have to move in space.
Yeah.
In
No.
space, it's gonna move in time.
Yeah, but not like how the difference of how you measure this, like this and this.
I don't think I understand your question.
like what is the difference between this length and this length?
One we can see, one we feel.
Yeah, but it's hard because this is very abstract, everything. The difference is this is dos D, no? This length is dos D, dos D, 2D, and this is 4D. No, we said it. Now it's 4D. So you can calculate this with the Pythagoras theorem because it's 2D, but what I said before, you cannot apply high school geometry to 4D. So this length is calculated very complex because it's like very complex mathematical to calculate 4D. To calculate like the movement, no, from here to here. So this is literally time. Time is just another distance. You can think of time as a distance. Like, you know, you are here and in the future you are in another distance. Yeah, as I told you, like nothing is correct. No picture is correct of 4D. But no, you have here 3 dimensions plus 4 dimensions. So yeah, and also like this they say it's invariable in every point of view. This is always 10 meters. It doesn't matter if you like turn it like this or whatever, it's always 10 meters. This also is always 10 seconds. It doesn't matter the point of view. From every point of view, this is 10 seconds. So this is what they said is the only objective, you know, subjective, objective. So they say this is the only objective things of the universe. Because it's the only thing that doesn't depend on any point of view. From all point of view, this is the same length. It doesn't matter from where you are looking at. So this means that like we don't know which time and which space it is going on, but we know it happened. It's the only thing we can't know about the universe, that it is happening something. Very abstract also, I guess. Okay, let me see if I'm missing something. No, I think it is. Okay. So also like a very interesting conclusion uh, from this perception of time, according to Einstein, is that like the same way space exists, all the universe, no, all the space of the universe is existing, no, right now. Like right now, the kitchen is existing, no. This room is existing, the kitchen is existing, your house is existing right now, no. Like in Mars is existing, no. All the universe is existing. So the same way the space is existing, time is existing all the time at the same time. So the human division of past, present, and future is just that, what I said before, no? It's an artifact. But according to Einstein, there is no division. All the time exists at the same time. The future exists, the past exists, the present exists. So, as you can imagine, if the future exists, why the fuck are we making choices? This will be another philosophical session, if we are free or not. This is one proof that we are not free at all. There are other proofs that say we are free. This is one of my favorite topics also. So also like why I think this is true also, because for me the history of humankind is the history against our ego, because we can see a lot of time in human history we thought we were the most important thing in the universe, no? 1000 years ago we thought we were the center of the universe, we thought everything rotated around us, we thought we were special living beings, no? And the gods created us, especially only for us, everything. We thought time depends on our perception, no? But as we learn, we are not special, we are not the center, nothing rotates around us, no? So for me, it's the same. Now we are realizing like time doesn't depend of us. Time is something universal. It doesn't matter if we think something is the past of the future. Obviously, the universe doesn't care what we think is the past of the future. Time is like a unity, is not a human division. So this is why also I like this theory. It goes against human ego, not that we always think we are special, everything depends of us, but I don't think so.
But it makes me think about, like, you know how two people can be sitting in the same room doing the same event, but their perception of how much time has passed is completely different. Like, yeah, it's kind of a thing of point of view and the perception of time being different, but in its essence, it's still the same.
No. What do you mean?
Like, you said no matter from what point of view you look at time, it's the same.
No, this length is the same.
Yeah.
No, but not time. Like, from your point of view, maybe it was 11 seconds. From my point, it was 9.
Makes sense.
But if you calculate it, it doesn't matter. It was this.
Yeah.
But this is very complex. Like,
so it's different. How to say? Different type of time. In a sense, that's the measured time and time as a.
Yeah, you
maybe
can say
general.
human time, universal time.
Yeah.
The universe doesn't care about us, obviously. It doesn't matter what we think of it, it's gonna happen. But the thing about this is like you perceive it at 9 seconds or 11, but the only thing you are sure is this happened. All the point of view show something happened. Like for example, no, all the point of view show the ball fall, but from you calculate it took 5 seconds, you calculate it took 6 seconds, but you both saw the ball fell because something happened. So this is the objective thing about the universe, that you can say like something happened.
But what if sometimes within the universe 10 seconds are one length and the next time 10 seconds is a different length? Like, do we have a proof that that same amount is always the same amount? You know what I mean?
Like, I think I know what you mean. This is how have you heard about the dilation of time?
Yeah.
You know, like if you go at very fast speed, you like have you seen Interstellar? No, when they go to the planet with the high waves, no, for them it was 1 hour. For the guy on the ship was 30 years. So this is a little bit about this, because yeah, this is hard. Yeah, you can think like space and time. You can think of it: if you go fast on space, you go slow on time. If you go fast on time, you go slow on space. So yeah, you have to choose. Like if you go fast on space, you take speed from the other one. If you go fast on time, you take speed from space.
So if universe is not moving at a constant pace, then its measurement of time would change, right?
Yeah, the universe is very weird because they say the universe is expanding faster than the speed of light, so they don't know why that's happening. Even I think, yeah, this is very weird. Also, there are like two things, like dilation of time and contraction of length. Also, if you go very fast, and I'm holding a pen, if you go at 10 meters, you see it's 10 centimeters. If you go at 1,000 kilometers, you see as 9 centimeters. And both point of view are correct. As I said, the only thing true is both show a pen, but you cannot be sure how much the pen is. But if you have 2 point of view, with this equation you can calculate, I think, like the real length, because you can compare both and you can see like why one see this and why the other see another. But this is hard. Okay, so this is to see if you understand space-time. If you travel to the past, where would you appear? Like right now. You go 1 year into the past, right now, in that chair. Where would you appear?
I don't understand.
Depends how time travel would work.
But where would you think? Right now, you travel 1 year into the past.
Like I would be where I was 1 year ago.
No, like, yeah, and where is it? Where were you 1 year ago?
Somewhere in Latvia. God knows, I don't know.
But you travel to the past.
Yeah.
Like you are right, like you don't move right now, and you go 1 year into the past. Are you in this room or not?
No.
Where are you?
The space changes.
Yeah. So where are you?
In the past.
But in which place in particular?
Like it differs for every person.
Remember, like everything is moving. So where would you appear? In the middle of nowhere, no? Literally in the space, because the Earth has moved, the Sun has moved, the Milky Way has moved. So if you only travel in time, you appear in the middle of nowhere, no? Like in the space. But this is why, according to Einstein, there is not a space and time, is a space time. You cannot separate time and space. It's always together. So in reality, when we say time travel, now the accurate term will be space-time travel. You cannot travel in one without traveling in the another. So this is like a thought experiment to understand, like time and space are always together. You cannot separate them. So also for fun, like, do you believe in time travel?
So if you think like that, our past is gone as a way of looking at space. So if the time is gone, then space is gone too. Like that's how I understood.
Gone?
your
What do you
explanation.
mean gone?
Like if you're in the nowhere, then what I lived is not the thing that I think it is. I don't know, like.
No, like your like this room hasn't disappeared. It's in
Yes.
another space-time.
Okay.
But it's not just because it's not just like the Earth is moving around the sun. Also, the sun is moving around the universe. So, like,
That's changed.
yeah. So this room is in another place 1 year ago in the universe.
Then I can travel to the past or future. I don't know.
What do you think about time travel?
Like, I'm open to the idea because it could be that, as with dimensions for these things, there are dimensions for the general experience that we can have as humans or souls or whatever. So, like, yes, you can't do that in the kind of physical space that we live in, but maybe you can do that in a different sort of a space. You know what I mean?
No.
Like how people believe you can do it through astral projecting or dreaming or whatever.
Yeah, like having prediction, no?
Yeah.
But it's not the same as time travel,
Like sort of depends how realistic your experience is.
Yeah, but it's not like you travel to the past and you are like, yeah, like.
Who knows what the monks experience? Maybe they actually go on meditation, they travel into space and the time and break all the laws of the universe.
Could be, like, you never know. Like, what seems impossible now in 100 years, it's totally possible.
Exactly. That's what I'm saying. You don't know.
For me, I don't believe. Why? Because, as I said, if the future exists, then time travel exists already, no? If the future exists, it means they invented time travel, so time travel exists already. But if it exists, it means we should be seeing people, no, from the future coming to us because it exists already. So if we don't see anybody coming, it means it doesn't exist. But the opposite is the same, no? If the future doesn't exist, then we can't travel to it.
But like if the future us cannot travel back to us, so you're thinking about that. But the universe is changing too, so maybe we could travel from here to future, but not like future to here, because in future the universe changed already and it's not possible there, but here it is.
Why? It changed also, no?
Yeah, it's changing, but the way it changed is possible for that now. Like I'm literally thinking about it, but it could be like that. You could go to the future, but cannot come back, maybe in that way. So could we really say no? This can't happen.
No, we can't say that.
Right.
But also, if we take the same thing as said previously, maybe there is future and there is time travel in future. Maybe it's even now, but the way I said it works from a different sort of dimension, and we do experience people coming from the future, but we cannot access that dimension right now. So we don't know that they're coming to us, but they are, and we experience it through other things, like through the dreams, like through the whatever weird experiences we're having.
Could be, no? Like there are international laws for time traveling. Many movies are like this. There have to be many laws. Like people can't know you are traveling to the past because if not, or
Yeah,
to the
not,
future.
no, not just that, but as I said, that as it's not possible in this, like the way the time is space is the way you said it, that like if we travel in time, then it means that like everything has already moved, so we're in the middle of nowhere. That's why I'm saying maybe the time travel is completely different. Like it's not about moving in the physical space as we know it, the moving universe, but it's like on a different dimension that we're unaware of. So when someone's traveling from the future to you, you might experience it or you might not notice it at all, or you experience it in subtle things just because you don't have the capability to access that dimension. Yeah.
Could be. Yeah. Could be. Who knows? Okay. No, yeah. Okay, this is another image I created to imagine a 4D universe, but as I said, all the images are wrong. Okay, so here we have 3D space. No, this is, you see like a 3D rectangle. So the way I picture this rectangle is you take the whole universe and you pause it. Like you hit pause like a movie. So this is the universe, no? It's in t equals 0. You can say 0 seconds. This is time equals 0, no? But not that there is no time, just that it is paused. This one is instant, no? Like a photo. You can say also you take the whole universe and you take a photo. So this is the universe. Now you unpause the universe and there is 1 second, no? And then you pause it again and you take another photo of the whole universe. No? So here we have the 3 dimension of space and here we have the 4 dimension, no? So for me, time is a little bit, yeah, what's in between, no, one photo and another. You can say also like a movie, no? What's between one photogram, one photogram and another photogram. No, like there is nothing, but you perceive it as movement, no, a little bit. Also, we don't know if there is like a final limit of the universe, if you can divide the universe in instant, or there is never nothing in between. Everything is a continuous space. Yeah, and this is like one way I have to picture it. Yeah, this means a lot of things, and this energy here is the way I picture, no, like the transition from one instant to another, no, because the matter, no, move from here to here following these rules, no, it's not like random from one instant to another. It follows these rules, these 4 rules, all the atoms in the universe. So this is why if we are here, no, we can understand this instant because it leaves like a footprint, no. So we, like here, no, like I don't know, like another example is archaeology, no, like we can understand the past of the earth because no, it has left footprints that follow this. So through the logos, we can understand it because it's the same rules all the time. And this is how we study the past, no? Because as I said, no, the time is everything. Time is not like the past is not destroyed and the future is not coming. They both exist. So this is why we can understand the past, no? Because we can analyze the footprint of the universe in the past. Yeah, also this is yeah, we spoke, you were here with the mind, I think, or who knows? Whatever. Like this is how I explain mind and memory